we will share it. We need to check it out. No, this one. This one. I hope it works. Maybe. You want to have this one?
Yeah. It's online.
To those who are online, can you see the presentation? Just say anything, please. Yes, Adam responded. Perfect, thank you. No, this one. This one. So
let me check.
Yeah, perfect. So it's my pleasure to welcome here Professor Shiping Ning from National Chongqing University in Taichung. A colleague of mine, we've been started last year with the collaboration. I am very pleased that one of our PhD students is there. He came in Taichung in January.
Yeah, this January.
And he's collaborating with Professor Ling on some certain applications, which I suppose will be now presented.
Yeah.
Here. So, Vivian, it's my pleasure to have you here. The floor is yours.
Okay, thank you. Okay, thank you for Professor Hazard's inviting me to be here. Actually, this is my second time at Brno, Brno University of Technology. Yeah, and right now, like Professor Hazard mentioned, there is a student, Aidan. Aidan should that. Actually, I don't know how to pronounce his last name correctly. But anyway, he is doing part of his PhD research in my lab. And also today I will include part of his results in today's lecture. Okay, so today's lecture, actually, I talk part of nanotechnology. And I changed the title a little bit. I will talk about the neuromorphic device first, and then move to the disease diagnosis. The first, actually, the title in our program, I talk the biosensor first and move to the neuromorphic device. But today, since the flow will be a little bit different, so I would like to share the neuromorphic first and then move to the biosensing part. So my name is Shuping Ling. You can call me Vivian, like Professor Haza or other colleagues. They just directly call me Vivian. And because why I talk about my name as a Vivian, you can call me, because in Taiwan, actually, there are a lot of professional researchers. They have the same name, exactly the same name as me, Shuping Ling. Yeah, so if you just log into the NSTC, one of big funding organization, government funding organization. Actually, you will see a lot of researchers. Their name is Shuping Ling. Okay, so my background actually is biomedical engineering. Right now, I am affiliated in Graduate Institute of Biomedical Engineering, and so let me just quickly let you know the geological location of Taichung City. So the National Chongqing University actually located in the middle of Taiwan. So the city actually is Taichung, means the middle part, middle city in Taiwan. Yeah, and so the the university actually founded based on agriculture. So we have a very good agriculture or vet department in our university. And also it recently we have another new department, new college, the new college of medicine, medical school. So recently it is a complete university. And also in our main campus, we have several interesting things. Like we have a lake, and one of the small lake, the biggest lake actually is the map of China. And another smaller lake that is Taiwan. So it is kind of the originated land why we have the university name as Zhongxin, because at the beginning, they think in the future we are gonna unite with China. Yeah, so it is a funny story actually. So we also have several other campus. So we have some experimental forestry campus. And also inside of that campus, there are some hot springs. So if there is a chance, you can visit us. Yeah, and but I need to say, next February, I will be transferring to another new university that is located in Hsinchu. So just let you know the geological locations. Yeah. So I'm gonna move to the part of the introduction to my lab. So my lab right now, we have two different main research directions. One is nano-micro biosensors that include today's topics, the solid-state transistor used in biomedical sensing or biomedical application. And the other part is the nano biosensor. So I will talk about how we fabricate the nano biosensors later. And of course, there are other different kind of application. If you are interested, maybe we can discuss later. And another part of my research interest is nano topography of the. You can use this nano topography to make some different kind of applications, such as you can make the surface with different topography. They will have different performance. Like you can put them into the sensor surface. And one of my students' application, he made some different structure of nano surface and try to use this nano surface as a platform to guide the injured nerve regeneration. So those are part of his research. Basically, we have some technique to create some
So how did it go
structure
yesterday?
on the surface.
Not good?
Okay. Actually,
Let's go so the lady can talk. It's
Need to switch them. Somebody. I see. Okay. Sorry. This one. Yeah. Go ahead.
So those are another part of application in my lab. You can create different nano surface for different purpose of applications. And so the first topic of today's lecture, I would like to talk about the transistor that we name it as the neuromorphic device. Actually, a lot of people in this room, maybe you know the application of transistor. But here I would like to share different perspective for the device. So here I made some table, just let you know the comparison. You can compare the transistor as a biological neurons. So most of you may know, like transistor, you can put them, you can apply them as a control, and they actually they have a similar function as a biological neuron. They can have a memory performance. And so here, just let you know the differences. For the transistor, actually, the conduction inside of the transistor is purely based on the electrons. And for the biological neuron, actually, it contains the electrons conduction and also some chemical conductions. And for the comparison for the speed, you can see the transistor right now. Actually, the novel transistor, you can see like around 800 gigahertz. So it's quite fast, the response time. And the biological neuron, actually, it is a little bit slower, typically around like 100 meter per second for the conduction velocity. And for the function, the transistor in the electronic application aspect, you can see you can apply them as a switch or apply them as a logic or do the signal application and so on. And for the biological neuron, you know, it's quite important in our living body because they will help you to communicate with external environment. You can through the neuron to perceive the external environment, give you some feeling, some sensing, and of course, the most important thing is they have memory function, and they can help you. You can through the neuron to learn the things from outside. And if you compare these two different, one is electronics, the other is biological substance inside of our living body. You know, the transistor, actually, right now you can make a chip contain around like billions of transistors inside. And for the neuron, actually one neuron, they may have other connection with different kind of neurons surrounding them. So it is extremely high density. They have a lot of connections, almost hundreds of trillions of synapse or synapse. You can pronounce another pronunciation, synapse or synapse. So one neuron may have almost 100 or almost like billion connection with external surrounding neurons. So for the efficiency, of course, right now, a lot of research on how to reduce the power for the transistor, for the IC. And also, you know, the neuron, because when you wake up, your neurons start functioning. You can perceive, you can have some feeling, you can perceive the external stimuli and to know what's going on outside of the world. So there are more, the power consumption actually for the neuron is lower. So here just let you know the differences between the neuron and the transistor. Right now in my lab, we are trying to find the transistor to sort the transistor function and try to sort them to find the comparable neurons. So we call those devices as a neuromorphic device. And so how to make the transistor? Actually, the conventional way, you can use the silicon-based fabrication process. And in my lab, we use the 2D material, and we use another technique we call mechanical exfoliation method to faster fabricate, to quickly fabricate the device we want. The reason why we didn't choose the silicon-based, here are some summary I did here. Because the silicon-based fabrication, there are some, actually there are some pros and cons from these two different fabrication process. For the uniformity, of course, the silicon-based, they can provide better uniformity for the entire device made on the silicon wafer. But for the material, actually, there are limited material resource you can use on the silicon-based fabrication process. And this is the one of reason why we choose the mechanical exfoliation, because right now you may know there are a lot of different kind of 2D materials in the world. And it will be easier for us to quickly apply those 2D material and make them into a device, and we can quickly test their performance to know whether this transistor, this device, can be a good candidate as the biological neuromorphic device I look for. So for here, you can see for the cost. Of course, if you are gonna use the silicon-based, change the parameter for the fabrication process, it will cost a lot because you need to find a suitable parameters. But for the exfoliation method, you can simply apply the advanced 2D material and build a single device and test it. And there are some limits for the 2D fabrication. Like this 2D fabrication process, usually just only the single transistor, single device will be okay. But if you are gonna have a larger scale fabrication, that is almost impossible right now for the 2D fabrication process. But again, it is a simple way you can directly apply 2D material and integrate the 2D material to fabricate a single device to test their performance. And also it can help you to quickly know some of important parameter. In the future, you may change some of fabrication parameter in the silicon-based fabrication. So for the summary of pros and cons for these two fabrication, like the scalable, reliable, high yield, those are the pros summary for the silicon-based fabrication. But for the 2D material, they have some unique advantages, such as they can accelerate silicon innovation and also give you some parameters. Maybe in the future you can apply in changing the parameters in silicon-based fabrication process. And for the cons, of course, the silicon-based fabrication rigid and costly to modify for new concepts. And 2D material, because the scalable problem, so there are some and also the reproducibility, there is another main problem for 2D materials. And also if you are gonna integrate the 2D material with the conventional silicon-based fabrication process, it is another problem. But again, it will be the feasible way. In my lab, we use the exfoliation process to fabricate the solid-state transistor. So for the 2D material, actually, when we use the mechanical exfoliation to stack all the 2D layer together, between all of those 2D layer, there will be some van der Waals force to help you to integrate all the 2D materials together. So that's why I say it is the simple way. You just pile up all the different layer of 2D material together, then it will become a transistor. Of course, you also need to do some further fabrication process that can use the e-beam writer to deposit some contact electrode and then you can measure the device you make. So for the neuromorphic device, by using 2D mechanical exfoliation methods, we come out several results, such as we used different 2D material, MOS2, HBN, graphene, or HFS2, or INSE, and so on. Those different properties of 2D materials. We can come out some unique transistor, unique properties of transistor. And all of those transistors are based on the mechanical exfoliation method. So all the layer, they will stack together and make a transistor. So it is a easiest way in my lab to fabricate solid state transistor. And those are some of our recently published results. And today I will focus on two devices. Later I will introduce, we published two different devices this year. And also I will talk about how you apply them. So the first device is we apply the 2D material transistor in biosensing, specifically in the tactile sensing. And actually, we found the transistor we made through the mechanical exfoliation method. We found when we choose the specific 2D material, they will come out some spatial performance, like the spatial receptor exists in our skin. So that's why we apply this device as a tactile sensing. And so let me just quickly talk about the tactile sensing, and later we will let you know the device performance. And so we, at the beginning, we think the transistor performance, they have a very unique property like the previous, the graph shows you here. Actually, they perform, their performance are very similar, mimic to the receptor electrical signal in our living body. That is the it is kind of mechanical receptor. We call it as a Merkel receptor. And this Merkel receptor, everyone has these receptors in your skin. And especially for the blind people, they can touch the dots. They can perceive the information through the braille, so they can communicate with the external environment. They know what's the meaning for this sign. So the reason, the specific function for this receptor is they have an inverse notch filtering effect, and also they can inhibit other noise. So we call it as electro inhibition for this receptor. So this is the biological Merkel disk. They can enhance the main signal. So we call it as a inverse notch filtering effect. And also they can inhibit the other signal, so that when they suppress the other signal interference, they can let the people to sense the main signal more significantly. And for our device, our neuromorphic device, they have very similar performance like the biological Merkel disk. So that's why we think we can apply this device as a tactile sensing application. And so the intelligent sensor for tactile sensing right now, there are a lot of different devices recently invented. specifically, they can help you to transform the external stimulation into the electrical signal. And this electrical signal will be transduced to your brain so that you can understand, you can realize what's the external environment. So this is the concept for the tactile sensing. And as you may know, in the biological system, all this electrical signal actually combined with some chemical reaction. You need to detect the chemical reaction, like this is another neuron. When they pass through the signal to the following neuron, there should be some chemical reaction. And this chemical reaction will further turn into the electrical signal so that you can let the electrical signal further propagate to the brain. So your brain can perceive the external environment. And so basically the tactile sensor, they should detect external stimuli and convert them into the electrical signal and modulate the received signal by cognitive processing. So that's why we think about our device. If you can find a suitable transistor, you can make them as a neuromorphic device, such as in the tactile sensor or some wearable electronic device. And so this is the topic I just show you at the beginning. So the device, actually, they are mainly composed of transistor. So this transistor, you can give them the stimuli input through the gate, and they will convert the stimuli into the current conduction, and then you will record the output signal. And this signal you can further process the signal, and they will give you the result for this specific device. They give you the different performance. They have a inverted notch filtering performance, and also the surrounding external stimulation will be suppressed. So that's why we think this may mimic to our biological Merkle disk, the function of the biological Merkle disk. And the device actually contains 3 different 2D layers. For the middle part, this is made of graphene, and we use this graphene to trap the electron. So this device actually is a floating gate field effect transistor. And the second layer actually is made of the HBN, and this is the insulator. And the channel device, we choose the MOS2. So when you apply some stimulation through here, you can change the conductance for the channel. And the output of the current will be further measured so that you can see the transistor performance, electrical performance differently, and also sort out spatial device through this process. And all of them are stacked together, so we call this structure as a van der Waals heterostructure. This is the transistor I mentioned. They have similar function as a Merkle disk, biological Merkle disk. And of course, usually after you fabricate the device, you will measure its electrical performance. And also because it is a transistor, they have a memory function. So you can test their endurance or know what is the retention for this transistor. And for the electrical characteristic here, I forgot to mention one important thing. So this device actually here we change some structure. So we intentionally create the SS region right here For the conventional transistor, actually the 3 layers will be almost the same length. But here we intentionally integrate space. So we call it as an access region because we found after we make our device with those access region, the conductivity will be different and they will perform the inverted notch filtering effect. So this is the spatial structure we created here. And here is the electrical characteristic. For the conventional one, actually the on-off ratio is quite high, almost 10 to the 6 order. And also this is the conventional device. And if your device have the access region, they could also have a pretty good on-off ratio, but almost a 10, one order less than the conventional one. But and also there is a spatial trend. In here you can see they will for the conventional one they will reach plateau quickly, and for this one when they reach the saturation region, there is a slight differences. And for their electrical performance, actually they have pretty good retention and endurance as a conventional one. And these two actually are the conventional electrical characteristic. They have a good performance. And the previous one I show you here are the device with the access region. They also have a good retention and endurance properties. If you are gonna apply them as a memory device, they are good. They are also good and suitable for memory device application. And so we further investigate, could we change some electrical property? Could they be a neuromorphic device? So we investigate their neuromorphic behaviors. So the neuromorphic behaviors here we define as could we change the when we have different external stimulation, could they respond to different stimulation? So we call it as a plasticity. So the plasticity actually in the biological neuron, this is a very important property. Since this plasticity, we can learn and memorize something. And for the transistor, if you are gonna name it as a neuromorphic device, they should also possess those plasticity function. So from the plasticity, we changed we did some tests, such as we changed the external stimulation spike amplitude, or change the spike duration, or change the spike number. All of those stimulation parameters result in different electrical performance. And the right-hand side here shows you if you integrate the access region into the transistor structure, you can see they will have the inverted notch filter signal. Like, sorry, this is the notch transitional notch filter signal. So because of this reason, so we find this will be a feasible way for us to apply this device as a tactile sensing application. And so this is the conventional one. From the conventional one, actually, when you increase the spike number, usually the memory will going high. So we call they have a you can see the output current would increased. So they have facilitated stimulation results. And if you compared with the access region, Actually, the degrade time here shows you for the SS region, their degrade time will be slower compared with the conventional one. So here just give you a summary about why we can come out the different kind of plasticity results from the SS region device. That's because through the SS region, they would limit the electron transfer and also limit the accumulation electron in the floating gate so that you will get the inverted notch filter effect from your device. And we further apply the device. We made 25 individual transistor, make them as an array. We integrate each device with a pressure sensor, make them as a touch screen. And this touch screen can show you, once they receive appropriate stimulation, they will come out different pressure signal. So this is the inverted notch filtering signal. You can see if you want to come out the inverted notch filtering device, you may need to use a lot of different electronics components to build up a circuit. And this is the real circuit components. They would result in around like 11 hertz signal. And this is the signal comes from our device. And you can further use them as a tactile sensor, and because they can help you to suppress the external unnecessary signal stimulation. So unnecessary stimulation, so they have electro inhibition characteristic. And also this device, if you want to use the conventional electronic component to build up a inverted notch filter circuit, it is quite bulky. And through our fabrication using 2D materials, actually the entire area is around 225 micrometer square. It is almost like 2 or 3 the diameter of 2 or 3 of your hairs. So it is quite compact. So this is another advantages of using this device. And also the response time is quite high. So after they sense the signal, their recovery time is around 0.43 seconds. So this is the first device, neuromorphic device. And the second neuromorphic device, we apply this device as a neuromodulation. And actually, the device design is quite similar to the previous one, but here we add another gate. We further apply this device with dual gate. One is top gate, the other is from the back gate. So you can make this device, they work differently. So we call it as a neuromodulation. And this work, actually, agent participate in this work. So here I'm gonna talk about the another new design. So the conventional dual gate device, actually all the channel and the floating gate, they have the same length. But for the SS region device, like I mentioned, actually the floating gate, they usually are not really equal to the channel. And for this application, we also add another top gate here. So they will perform differently if you compare it with the previous study. So we further apply the device. First, we also check their electrical characteristic to see whether it is suitable to be a neuromorphic device, to see whether they can respond to different external stimulation, and define whether this device has a plasticity characteristic. So from here you can see even you change the external stimulation, the different voltage stimulation, or change the numbers of the stimulation, you can see different response. So it means they have the neuromorphic device property. And also we found when you integrate the top gate, you can modulate the channel conduction. So you can let them have a long-term potentiation signal, like here, or short-term depression signal. So that's why we name this device. They have another function we call neuromodulation behavior. And also apply this device, you can make them as a logic gate application, such as this device, they possess the NOT gate and the OR gate. So you just simply apply the top gate or back gate. You can change their application. So just give you the quick summary for the transistor part, then I will move to the biosensor part. So for the transistor, actually here we try to find the suitable transistor that possess some plasticity as a biological neuron. Usually those plasticity you can observe from their amplitude stimulation, or from their duration, or spike number, to know whether they can respond to different stimulation in your device. And also for the slow adaptation, like the SS region, for those devices, they have pretty good slow adaptation, very similar to some of neurons in our biological system. Actually, there are several different types of neurons in our living body. Some of them, they can respond quickly. Some of them, they respond slowly. And for the device we fabricate here, if you integrate the SS region, they have a slow adaptation property. And also from the first device, they also possess the inverse notch signaling response. And also because you can make that, and also electrical inhibition, so you can apply this unique property to enhance the signal, the specific signals. And also because you can make them very compact, so it is a miniaturization for this device, and you can make them. They can sense the stimulation and also localize the stimulation. So they can do some spatial discrimination to put, if you integrate this device with the robot, in the future, you can let the robot feel the wall very similar to like human being. And also the device, if you also integrate with the top gate, they will their performance will be differently. You can modulate their response, so it could give you the neuromodulation applications. And the second part, I'm gonna move to the biosensor. The biosensor we used here, we create some nanobrush structure, and we apply this structure to different biosensing applications. So how to fabricate the nanobrush? We use the MACE etching, that is the metal ion assisted etching, chemical etching process. So we prepare the silicon wafer. After wash, use the MACE process, you can get the very vertically aligned nanowire. And you can use the KOH with IPA solution to reduce the nanowire density. After you reduce the density, it depends on your needs. If you want to sense like micrometer scale material, maybe you can make a very dense structure. And if you want to sense like a nanoscale material substance, maybe you can make them like a nanobrush structure with some distance. So after you make those needle structure, you reduce the density. You can further coat it with some conductive material. Here we choose the ITO. Of course, you can select other conductive material, like you can coat with the polymer, conductive polymer, or some metal materials, just to make sure they can help you to transmit the signals. And of course, we also do the annealing in the end. So the bottom image shows you the SEM. This is just etching, and then you can use the KOH to control the density, the needle density. And after you find the suitable needle density, you can further coat it with the like ITO we choose here. So after that, you will get those brush structure. And the following lecture, I will introduce you to application two main application. How we use this nano brush structure in biosensor. So the first part is we use the nanobrush structure for bacterial detection. So actually the bacteria, they have a cell wall. The cell wall contains different liposaccharide. Those saccharide, you can, based on different liposaccharide, you can further classify the bacteria as gram-positive bacteria or gram-negative bacteria. So the device we developed here, they can distinguish the gram type of bacteria. And in clinic, if the doctor knows about the gram type bacteria, they can quickly select suitable antibiotics to treat the patients. And in this research, actually, we add some different bacteria inside different sample. We apply this sensor to in food application. So how to choose the suitable density of nanobrush? Actually, we did some literature survey, and we found there is a theory they can help you to get a rational design to find the suitable density of nanobrush structure for your experiment. And here we just, this is a scheme for our study. So basically for the cell wall, they have different polysaccharide. And the surface of the nanobrush, we will further do some chemical modification. And here we use the Brno acid because they have two diol group. They can interact with the polysaccharide. And since different gram type of bacteria, they have different extent of the polysaccharide on their cell wall, so you can distinguish the type of the gram bacteria. So basically, those are part of those are more relevant to the chemical. But again, this might a good application for us to further apply our nanobrush as a biosensor. In this study, we use the electrochemical detection method we call the impedance to measure the resistance, the total resistance differences, and to show us the sensing results. And the theory I mentioned earlier for us to control the suitable density of nanobrush is this one, SDLVO theory. Through this theory, we can know, we can judge from the interaction force between the nanobrush and the sensing target and choose the suitable density of the nanobrush. And those are some results. And also, of course, you can do some chemical modification to reduce the surface forces. When the surface forces are lower, you can there will be higher chance for your for the interaction, higher chance of you will get the interaction more significantly when you sense the analyte. And before we see the results, I would like to let you know how we interpret the signals. So basically, we use the impedance. We will get this semi-circle signal with a linear line. And when you measure the semicircle, then you can define the resistance. I means the solution resistance, and for the RCT means the charge transfer resistance. And also there are those signals can help you to know the equivalent circuit. So when you sense, basically you can measure and compare the parameter shows you here to know the signal you sense, to interpret the signal you sense. So here is the result. Actually, we choose two different representative bacteria. One is Staphylococcus. This one is gram-positive bacteria. And E. coli is gram-negative. So we apply these two bacteria and do the sensing. We found our sensor can respond to the gram-negative more significantly, almost 54 differences compared with the gram-positive signal. Therefore, we apply this device for the real food sensing. And this is the result. You can also reuse this biosensor through different further process. You can wash out the interaction, because the interaction between the brownie acid we modify, we create from on our nanobrush. They will interact with the bacteria. Those are some electrical static force. So you can simply destroy this force and reuse your biosensor almost 4 times. You can get a pretty good response right here, sensing response. You can reuse them. And this is some results we further we confirm indeed we sense the bacteria. And those are SEM and also the sensing mechanism between the brownie acid and the cell walls of the bacteria. So when you use the higher concentration of the some reagents, you can destroy the interaction simply and reuse the sensor. And we also collaborate with another professor because they help us to come out of the readout system. So you can make this sensor, you can do some field examination outside of the lab. And another nanobrush biosensor we apply in the real human blood plasma to distinguish the Alzheimer disease stage. Usually for the Alzheimer disease examination, you need to use the MRI or use some other imaging diagnostic tool to know the stage of the person, of the patients. But here we use the plasma to quickly know the stage of the Alzheimer patients. Here just give you an overview about why Alzheimer disease are quite, right now in the elder people, you can see it is a blooming disease. You see this disease very often. And usually for the, if people suffer from some cancer, actually right now the cancer can be controlled. So it is not really deadly, one of deadly disease. Of course, it will result in death. But again, right now, a lot of advanced medical treatment can control the patient's progression. But the Alzheimer actually is quite, right now there's no efficient treatment for patients. Once this person has been diagnosed the Alzheimer, usually around like 5 to 10 years, this person will be died. So for the Alzheimer, actually there are several important biomarkers for clinical diagnosis. This is the normal neuron, and the right-hand side shows you the person suffer from Alzheimer. So you can see outside of the neuron, the brain tissue, you will see a lot of plaque. Those plaque would let the brain shrink. So eventually, this patient will lose some living function. And so those are the different kind of diagnostic conventional diagnostic tool like MRI PETs, or they need to use their spinal cord fluid to do some testing. Those are not really useful. So we discuss with the clinical doctor. They hope if there are some feasible way and they can quickly know the patient's condition, they can change the drug to treat their patients. So we further come out our application. Those are some treatment gap in the Alzheimer. So actually in my lab, we are doing the NFL marker. As I mentioned, there are some other proteins will accumulate in the brain, so and further make the brain shrink. Of course, these are another two important biomarkers that could help you to diagnose patients' condition in Alzheimer's disease. But in my lab, we use another marker we call NFL. So the NFL actually exists in a neuron. When the neuron start to have when the neurons start become abnormal, this NFL, the neuron filament, will start degrade. So this NFL will penetrate the blood-brain barrier and get into the plasma, the blood. So you can, when you withdraw the blood, there is some possibility you can detect the concentration of NFL and further know the condition of the patients. Therefore, if you have the biosensor, they are sensitive enough for you to pick up the NFL. That will be a good application for clinic, in clinic. So this is the NFL as a biomarker right now has been applied in several different disease diagnoses. And this is our the concept of our experiment. So we are thinking if because those biomolecules are nanoscale, so we are thinking if we can create a suitable density of nanobrush, there is a we can improve the sensitivity of the sensor. There is a higher chance to get a relatively real signal of an FL. So we did some electrical sensing, and we found, of course, the nano brush, how we select a suitable nano brush density. We tested with, we did some electrical measurement. We test it with the pH sensing, and also measure their response time. And after we modified with the antigen of the NFL on our nanobrush sensor, we can further distinguish different status, patient status in Alzheimer. We can detect different stage of Alzheimer disease in the patients. So here we separate into four groups. One is the control group. The other, you can see here with some subjective cognitive decline or mild cognitive impairment, and also dementia due to Alzheimer. So from the electrical signal, you can quickly distinguish the stages of the Alzheimer's disease within 2 minutes. And those further comparison, you can see the distinguishable signal if these patients suffer from the Alzheimer compared with the control group, the output signal, they will perform differently. Then you can distinguish their status. And these are the, we combine 45 patients' blood and do the test and get the statistic results. And of course, we also did other biosensor without the nanobrush. You can see the signal will be a little bit lower compared with the sensor. They have the nanobrush inside. And so this will be the application for the NFL detection, but we also, the doctor also interested about another topic, that is the exosome, because the exosome are around 50 to 130 nanometer. So, and they usually contain some RNA, microRNA, or some important biomarker inside of this vesicle. So the doctor asked me, could our nanobrush can also sense those nanoscale particles? Then they can further, they are interested about the inside contents. So we also create through our nanobrush, we can also catch some of exosome, the nanoparticle right here. And those nanoparticles, actually, you can elute those, you can remove those exosomes by using high salt solution. And for clinical doctor, they can further analyze the microRNA inside of those exosomes. So this is another application. And so just quickly move to the summary. For the further application, you would know you can apply those nanobrush sensor as a clinical diagnostic tool to quickly know the condition of the Alzheimer patients. And this is just some of the the video demonstrate how we do the measurement. So this is the sensor. In the bottom of this well, you will see the nano brush, and we just quickly measure it. Within 2 minutes, you will see the signal output. And so I cannot make them play quickly, but you will see the signal after you do the measurement. And of course, for the student, after they come out the signal, they will extract the data and plot it in their software. So here you can see the signal differences. And of course, you can also apply the sensor in different kind of applications, such as this one. My student applied this for the cardiac infarction examination. Just give you a conclusion for these two different topics in my lecture. One is select the suitable transistor for the neuromorphic application. The other is try to find the suitable density for different biosensing application. So those are nano-engineered platform that could offer promising solutions for next generation biochip technology. And of course, for the transistor, you can make them as a robotic sensing or use the nanobrush sensor for some advancing precision medicine. And this is some collaborated professors. And also I want to thank my students. And just do a little advertisement. We will hold another international conference next year. So if you are interested to visit Taiwan, you are welcome. And also you can let me know. You can get some discount. Okay, thank you. Thank you for all of your attention. Yes.
Thank you very much, Vivian, for a very interesting lecture. We are just a few minutes, but delay, but no problem. Just 1-2 questions for now, and then we can postpone it during the networking. So questions? Yeah.
Very interesting, especially the double gate transistors, because they can really act as neurons having more inputs. Anyway, my question is concerning the tactile sensor. You've shown precise details about the structure, and I wonder how much pressure you need to apply to get signal, or is it just working by proximity sensing, like you depolarize the gate when you your finger close to it?
Yeah.
Not sure about the principle.
That's a good question. Actually, I would say the device we create, they can process the signal. But for the application part, actually, for our device, we need to integrate with a pressure sensor. So it depends on the. Also, you need to consider the pressure sensor, how it could receive the pressure. So you need to look at the spec of the pressure sensor also. And for our device, I think they play an important role in signal processing. Once and the pressure sensor will connect with the backgate. So through the backgate, it will be the stimulation get into the device. And we measure the current through the channel from the source and drain. So further, of course, there are some limitations. And so far, for the pressure, we did not really measure how the range of the pressure applied in our device. But just a simple touch. Yeah, but for the specific pressure force, we haven't measured yet, but it's a good question. Yeah. Yeah. Thank you.
So if you do not mind, let's move for another lecture I think we will have enough time and
Yeah.
possibilities how to maybe more interact and to
Yeah,
explain
thank
some
you.
stuff. So
Thank you.
once again.
Yeah,
you very
thank you.
much. And we'll proceed with the next lecture.
Second one?
Is it the second one?
Yes.
Okay. Okay. Share screen. Okay, oops. So, next speaker is Professor Taiwan Kim from Bok National University from South Korea. It's a very pleasure to have you here and looking forward for your presentation.
Thank you. Thank you. Thank you for kind invitation. And this is my first visiting in Czech Republic. So I'm really happy to be here and Progress City. Then I didn't prepare any good map. Where is South Korea? Definitely, you guys know where is South Korea. It's very close to Japan, in between Japan and China mainland. So, actually, this workshop is really focused on the biochips. But unfortunately, I don't have any data on biochips. But I'd like to emphasize my material as well as the platform going to be useful for biochips. So it is not conventional. It's quite not that much normal. So my title is going to be a novel material and device platform towards next generation wearable electronics. I'm Teo Kim from, actually it is pronounced in Jeonbu. Okay. Jeonbu National University. It's very close to, it's the middle of the South Korea and southbound of the, it's the middle of the South Korea and it takes around 2 hours from Seoul. Yeah, this is I have a lot of data because this is really wonderful invitation in Czech Republic in BUT as well. So I'm going to start with my first talk lesson is next generation wearable device platform and move to I'm going to show you very interesting giant 2D metal nanosheet is a finger crystalline that it is definitely applicable for your biosensor as well. So and then I'll finish the summary. So actually, I have been working for 10 years in Korean Institute of Science and Technology. It is kind of the national institute. Then I have to move university in 2019. Then I'm just start my own work for 6 years. So I'm going to talk about the wearable platform. It's really oriented on device. Then I'm going to show you guys the nanomaterial, not nanoparticle, not nanowire. So I guess you guys are really familiar with nanoparticle, right? Or nanowire or nanorod. But I changed the idea. Then we grow very interesting 2D material, not actually MOS2 graphene. It's a metal. It's a single crystal. So this is my cartoon for published in a lot of different papers. Then I'm working really on the memory device, basically organic based memory device. Then I moved to change their structure is to be complicated from solid substrate to flexible. Then we can reduce the thickness less than 1 micrometer scale. Today I'm going to focus on these two papers has published in Science Advances as well as Nature Communications. So then this is our material. So those are two empty here. This is a metallic film, but it is made by copper named chip. It's a copper as well as we synthetic silver. It's a two-dimensional. The lateral side is more than 5. We can grow up to tens of micrometer, but thickness can be suppressed less than 100 nanometer. It's really two-dimensional. So here, so Professor Lin introduced a lot of important concept on electronic device. Then, so as you know, it's old one, right? CIT. I watched one CIT out there, the monitor, right? And sensor. So you guys are really interested in sensor. So in progress of a device, electronic device and their platform going to be integrated more and more. Then some people are working on nanoscale integration. Then you guys may expect the device going to be compatible with our human being. So the recent smartphone published in Samsung going to be foldable, right? Then some people trying to make sensor device on our body as well as clothes. It's going to be future, but unfortunately, the performance as well as the convenience is one of the important consideration. So still require both function as well as the shape of the device. So let's think about the performance. The main concept of a wearable device is gathering a lot of data from out of the body, from our body as well as environment. So when you go out, a lot of sunshine is going down, right? So you guys sometimes need the sunblock. No? No, yeah. So when you go into South Korea and Taiwan, it's a lot of sunshine. So women usually use a sunblock to prevent any sunburn, right? So, and a lot of signal from here, from body, is organic signal, as well as environmental signal, for example, humidity or UV light, the intensity of UV light and temperature. So those are really interactive device technology. So it means that the technology includes the processing, sensing, displaying, and memory transfer the signal from human body environment. So what I'm saying is when I usually enjoy learning. So last night I arrived here and it's cold, weather is really cold. I cannot get out. So I went to the gym. So I running 6 kilometers, but I use the iPhone app, watch. They count how fast I run, how many count, right? It's kind of interactive. Then the growth market is growing up because I have watch. You have watch as well, right? A lot of people have their own watch. So definitely the market is going to grow up. So and the performance, this is the emerging device, right? The requirement of future device is going to be high speed, small size, high capacity, and one more thing is building, convenience, and wear. So I talk a lot on this one to other professor who is working on clothes. If something is stuck on here, if you guys feel uncomfortable, nobody uses this one. So we have to consider both conventional current requirement as well as new requirement. So challenging, there should be a lot of challenges and a lot of paper you can watch. For example, here is you can attach your device on the skin, right? And well, as well as sometimes people trying to implant some device in your body to detect something. So here is a full electron tactile e-tactile system and material and their performance is one of the considerations. So I'm going to show up the recent progress of 5 electrons because the reason why I'm focused on 5 electrons is So our cloth is basically made by fiber. Each fiber is so going to be become some what is called textile, right? The conventional one is something like this because this is the conventional transistor structure. It's backgate. So when you use aluminum here, so you can deposit some polymer gate dielectric, and then deposit some semiconductor and source and drain. This one is a conventional 5-type transistor, but unfortunately, the scaling is strongly depending on the diameter of the fiber. It's really hard to minimize the size because recently TSMC in one of the Taiwan company trying to make a transistor less than 5 nanometer. But unfortunately, when you order any conductive fiber in Aldrich, is that they definitely the diameter going to be 150 or 200 micrometer. So the other one is people trying to make simple coating method on fiber because it is very important. So when you integrate any device on wafer is really flat, right? So you can use, or you have a lot of choice. For example, the simplest one is spin coating, right? How can you get that much uniform film on the fiber? This is an example. People use very narrow, tube, then coating, then they demonstrate this type of the prototype device. How about this one? This is they said this is urban-based memory array, but the quality is not that much good. How about this one? Waving, silky. The demand is really big. So recently, right before we publish our paper in Nature Communication, one of the MIT group published a paper in digital electronic fiber. But unfortunately, they use the fully fabricated chip. Then they just wiring by tungsten wire each other, then drawing. As you can see here, they make the digital fiber. It is composed of the storage program, storage and data storage and sensor, something like that. So how about this one? So do you guys use this one on your clothes? It's quite ridiculous, right? So here is a really kind of the next generation electronic textile beyond the waving technology. So I thought a lot on this one with my postdoc and my student. So this is conventional one. So you can see here, flexible electric device on flat surface, then you can exfoliate, then transfer on desired substrate, right? But unfortunately, right after delamination, so when deformation, something going to happen. For example, curing or delamination. So how about this one? This one is chromatic because we use one base fiber, then connect to each fiber as source and drain. But unfortunately, right after deformation, it also experiences the unexpected breakdown and poor electrical contact. Everything is screwed up. So we thought we required an innovative platform for wearable electronics. So the first step is I'm going to show up the very simple concept because it is a really conventional one because we integrate the 5-form organic memory transistor by using the conventional PVDF-TRFE, which is one of the conventional organic ferroelectric material. So we use the same concept. You can see here, this is gold wire. Then we calculate coating some PVDF-TRFE. But in this time, we embed very simple coating method that is called capillary tube assist coating in CTAP process. So you can see here, this is the wire, right? So we use very simple capillary tube. When you go to your laboratory, you can pick up any capillary tube. Then you can fill up any solution. For example, here we use the ferro PVDF-TRFE. then you can pull out this way immediately. The solvent evaporate, then we can get really nice coating and very uniform on the fiber. So let's think about that. This fiber is really one-dimensional, right? So we can really get the core-shell structure. Then the uniformity is really nice. When this is a bare gold wire, depending on the loading speed, you can control the thickness as well as the quality. Because we measure the capacitance at different size. So it's you can see here. So this one, the capacitance is almost same. It means that the uniformity is okay now. So you can see here is when you cut very carefully, you can watch the nice coating of the PVDF TRF layer out of the wire. So this is cross-section for right angle fabrication of the transistor. So you can see this bottom is the silver wire here. Then PVDF TRF is around 260. Then pentasene is one of the P-type semiconductor. Then the type board, it is a complete structure for transistor. Then we find out the beta page is one of the representative page to demonstrate the ferroelectric characteristic here. The performance is really nice because the ferroelectric is allowed the low operation voltage. Then we observe the really nice hysteresis window as shown in Professor Lin by using the MOS2 because MOS2 is just N-type, but pentas is P-type. It is turned on in negative gate bias. So retention is okay, cycling was okay. Then we carefully wrap our device on the tube, depending on different diameter. It was still okay. It's one of the examples. So this is video. I don't know whether it's working or not, but my student really shaking. Okay? So it's really hard to watch, but this is the one small wire through the sports band. Okay. Then we test a lot. In Princeton one, uniaxial strain as well as diagonal action. So the device was really working well. Then right after coupling, it's still working well. So it means that our device on the fiber is still working. The only requirement is we have to carefully sew in the scotch band. Then from this work, we are trying to make a neuromorphic fiber. So the device structure is very similar, but we just change the contact on the fiber. So here, this is a conventional ferroelectric fiber. We use the CTAC process. Then we can carefully coating the PVDF TRF here, right at the deposition of the pentasene. So unfortunately, the pentasene was deposited by thermal evaporator. Then we deposit gold electrode for source and drain. Then we can fabricate one gate and 1, 2, 3, 4, 5, 6 couple of transistors on the fiber. So you can think about that. When you apply some gate bias, for example, here is a pre-synaptic pulse, then the source end is definitely change the conductance of the pentasene. Then we can measure source and drain. It is called the post-synaptic response. Then we can measure the response against the pulse. So our concept is the difference in between two devices. For example, this is a free neuron, right? This is free neuron. Then it's going to be connected with the first neuron and second neuron. So we demonstrate this one is first and second, and there are third. We connect 10 transistors on the fiber. The performance is okay, as I shown in previous slide. So here is depending on the gate bias, we test a lot by changing the pulse width as well as height. So you can see here, we fix the gate bias at minus 30 volts because the pentasene is P-type. This is the potentiation and differential. So the nonlinearity is not bad because we can carefully control the gate bias. Then when you test the cycling, it was still really working well without any serious degradations. So we test a lot of But here we test a normal type textile array structure with one-dimensional organic multi-thread because you can see here, this is transist, right? This is transist. So we can connect each other by using the two conductive wire here, 1 and 2. They connect each other, source and drain. When we measure here, please note source and drain electrode, because those two is connect each other. Then when we potentiate first neuron and second neuron, the current, total current, the summation of current of both source and drain going to be increased. So we can calculate how is it working well. So you can hear, depending on the running pace, we can control each current level, summation of the current level. For this is an example, we use 1, 2, 3 fiber, then we connect two source and drain wire. Then right after submission, reviewer asked me, why don't you try it? Try this one. So my student connect almost 10 by 10 in the glove box. It's really crazy. So we can connect. We prepare 1, 2, 3, 4, 5, 10 fiber. Then we connect six of each. So we use 12 wire each other. So now it's time to measure. So we measure everything here. It displayed really nice switching. Then we calculate how it is really working well. Okay, so we test a lot of tests. For example, it's an MNIST simulation to recognize some image or sign, something like that. And also we test ECG pattern, processing. So we find out the maximum accuracy of our artificial synapse is almost close to 91% as well as 71%, both for MNIST as well as ECG. Definitely, it was the first demonstration by using the fiber platform for the neurofilament transistor. But unfortunately, our device system is not that much identical because we have to use very big scale because we use almost 100 micrometer fibers. So then we think a lot on what is really next, platform. So here is an example. Do you guys really think this is the future of mine? Maybe no, right? So I don't want to spend my time to study the computer system. So this is an old one, old story. What is next? So when you think about that, if you guys have any experience to go clean room, the semiconductor are going to fabricate in the wafer, right? So we can use a lot of different type of lithography system. For example, contact, mask liner, iron, whatever, and EUV. We can reduce the channel length less than 10 nanometer. Because my wife is now working in SK Hynix, it's getting a lot of money. So we use HBM for AI acceleration. So the scaling down is one of the important research topic for semiconductor. So I move this one to fiber. How? This is it is called a chip on a fiber. This is fiber, right? So whatever you think, when you watch any fiber, the dimension over here going to be 100 micrometer, right? 200 whatever. But even though the cross section is different, in macroscopic view, it should be fiber, right? Then, so we pop out new idea. We're gonna use this one. Oh, and then let's think about it that the radius is 50 micrometer. So we can integrate the electronic chip out of the fiber. How? Resistor, capacitor, and transistor. This one, as well as this one. The most important thing when you produce a semiconductor chip on the fiber, so anyway, you guys think coating the photoresistor, but we have C-type process. We can coating very uniform layer on the fiber. For example, photoregister. So we usually use AG, something like that, or so that is commercialized the photoregister. This is an example. So basically, we use the CTAC process, then carefully coating, because we use some core of optical fiber. The optical fiber core is definitely made by glass or quartz, right? It's a good substrate core, and it has really nice, surface, right? Then we coating the desired the polymer, for example, photoregister. Right at the coating, it's really hard to identify what's happening. But my student is carefully scratch out, then so we find out it's a nice coating on the surface. So we have tested whether it is really lithography, apply the lithography process. So you can see here, so right at the development, we find out really nice pattern, 5 micrometer, 10 micrometer, or 20 by 20 micrometer. So right after deposition of metal, for example, aluminum, then we do lift up a process. You can see here, we can get really nice pattern on the fiber. But unfortunately, it's really hard to make sure the focus. If we make sure the focus in the center, the other is weird. But we use very special lithography system that is produced by Heidelberg Instrument in Germany. We don't need any mask. Then we test a lot of different patterns to integrate different type of the transistor and sensor, whatever. So this is an example for the ring oscillator. So we're trying to integrate the 10 transistor on the fiber. This is the real image, but unfortunately, when you use fiber circular type, it is really hard to make sure the position. So we have to do a lot of overlay, the alignment, something like that. Sometimes it's rotate, right? So we have to use new one. It's circular, rectangular type fiber. So I Googled a lot of time. I spent a lot of time looking for the scale type fiber. So finally, I found the scale type core optical fiber. So we carefully sketch out the cladding as well as jacket. Then we did CTAC process. So you can see here, this is the filament. It's really nice, right? We don't need to spend the time to prepare the substrate. We just buy this one. Then we deposit all the chromium, for example, the electrode. Then we do photoregister coating. Then finally, we demonstrate the integration of any desired electronic device on the fiber. This is the result. So you can see here, this is glass, right? This is electrode. Then we trying to integrate the two different transistors with different dimension because we try to demonstrate the inverter by connecting two different transistors. So here in this time we use aluminum oxide because this is really high K. It doesn't require that much high gate bias. It is low voltage device. And the final structure is you can see here. This is top gate and source and drain. Then it is separated with the aluminum oxide for gate direction. Again, so this is the transistor and ring oscillator and inverter and capacitor. So because the fiber is really square, it's really easy to control. But unfortunately, we have to develop very careful and very useful holder system. Then again, so this is the procedure. So it required a lot of more than 50. So we coating a lot of CTAC process on the fiber. Then this is the final device here. This is opaque, and this is the SCM imaging. Again, so we integrate 10 individual transistors on the fiber, then connect each other. We demonstrate the ring oscillator, 5-stage ring oscillator. So this is a real image. So when you have a chance to visit my office, I have this one. I didn't bring any example here. but this is really flexible. So if you have any experience to handling any optical fiber, it's really flexible, even though it is made by quartz. So you can see here, this is the area that a lot of device is integrated from here. This is really key. So here, so we have a 4 phase, right? So on this phase, we integrate capacitor, UV sensor, as well as transistor, condenser, and demonstrator. So I think I need one more thing. So here we integrate the thermocouple on the other side. This is region. So unfortunately, we didn't make such a good condition for indium gallium zinc oxide, which is one of the representative N-type semiconductor. The mobility level is acceptable, but on operation it is still good. And this is inverter, and this is the ring oscillator. So all device, even though they are fabricated on the fiber, is still working well. Then, as you know, it's the indium gallium zinc oxide is response against the UV light, right? But we have a new idea. One more thing is because out of fiber, definitely the UV fiber, the changes are going to be detect the UV light because we use 470 nanometer here. So the off current is changing. So we can change the off current depending on the on and off the LED. Then one more thing is we connect the fiber with the conventional optical fiber. Then we monitor the signal through the fiber because our system is on the fiber. So then we find out the sensitivity is really nice compared to the UV out of fiber. So and the next one is thermal sensor. Actually, we deposit the very simple concept on TC1, 2, 3 at different position here. So when you right at the fabrication of our device, we put our sample on hot lab. Definitely the temperature is something like this gradient. So you can see here, if TC1 because TC1 is close to hot lab, definitely it's going to be hot. TC3 is cool. Then right at the measurement of the system, so we identify clearly the system, the thermocouple is really working well. So let's think about when you integrate this one fiber do everything, right? So we test a lot, it's bending as well as strain, and also we put our sample on the color and washing, something like that. It was still working well. So we imagine that. So by using our chip, definitely applicable for computer systems. So you can see here, this is the Intel Pentium process. It was published in 1996. I was the freshman in university. Then the system is really ridiculous because the system recently published one is a gigahertz speed, right? The process size is 0.35 micrometer. It's really huge, right? Then the transistor is 3.3 million. The most important, the die size is 91 millimeter scale. But this technology is really easy in listening, right? So I found out a new idea. Why don't you use this technology on the fibers, then calculate how long fiber we need? Definitely, we calculate it's simple mathematics, right? So we use 150 micrometer, then definitely it requires only 19 centimeter, potentially. But unfortunately, I don't have such a good machine and student, and one more thing is funding. So this is my future because the fabrication of fiber is really literally process, not batch process. When you go, the clean room, every process is going to be batch process, right? On the wafer, then it's going to move next machine. But our target is a continuous system. You can see here, photoresist coating by using CTAC process. Then exposure, I have no idea. We use the conventional mask-based lithography system. We have to develop this one. Then development and deposition, it should be easy, right? And lift-off process. Then right after inspection, I think I pop out this one. This is one of the schematics for continuous fabrication of the electronic fiber that is called chip on a fiber. So here is we just put one fiber, definitely it is working at computer system. So in chip on the fiber, let's watch very carefully here. Fiber is not alone. When you watch your clothes very carefully, so a lot of fiber is waving right together. From this concept, I pop out new idea here. Definitely, it is this system. Potentially, right? This definitely new electronic fiber system. Yeah. This is my first part, and I'm going to move second part. Unfortunately, I don't have enough time. I have to skip some part. Then definitely the two-dimensional giant metal nanosheet is synthesized for the first time in the world in our group. So before we invent this one, a lot of people synthesize only kappa nanoparticle, nano wires, no nano sheet or nano plate. So you can see here, I'm going to briefly show how to synthesize this one. So nano wire, right? It's point contact. It's very useful for the transparent electrode and silver nano wire as well, and nano sheet. So it is very completely different feature because I'm going to show you later, but this is a single crystalline. And this base plane is 1, 1, 1 plane. And when you start each other, this one is point contact, right? It may make plane contact. So when you think about the electroconduction, larger contact is better, right? Based on this one, so before we go further, so we study a lot on what kind of the method have been reported before we publish the giant 2D metal nanosheet. So people are really interested in the change their shape. It's a rice and fiber and cube or flower and rings or something like that. And some people report some micro scale nanoplate, but unfortunately it is really small. So it's really hard to use for the conductive filler, for example, nanoparticle or nanowire. So we change idea. People try to make small as possible. Okay, let's go different way where as large as possible to cover any desired substrate. So this is really simple because we follow conventional nanowire synthesis, but one of my students make a mistake. She put very interesting halogen material is iodine, then dramatically change their shape from 1 dimension and 2 dimension. So unfortunately, we have a lot of time to make sure the right condition is almost 4 or 5 years. Then now we got a really nice condition because halogen material is selectively absorbed on the basal plane, for example, 1, 1, 1. It is successfully suppressed the growth this dimension, and the nanosheet is grow only this plane. And the synthesis is really easy because I usually use DI water for solvent. We just put everything in the reactor. It is hydrothermal, or it is called sometimes autoclave, right? Then we can leave our mixture in the oven or heat it up to 100 Celsius C. This is the final product. We can now control the 1 dimension and 0 dimension and 2 dimension. We can control everything. So this is the image. This is the old one. I'm going to skip this one. So anyway, the dimension, when you actually watch this one, this is 111. And when you carefully cut cross-section of this one, this is 110 plane. You can see it's clear like this image. And one more thing is we can measure the EBSD. This is one of the two visualize the crystalline structure. So when you take an image here, definitely the base plan was only 111. So let's think what when you spray out this one is any desired surface, it is really easy to cover the surface because the dimension is really big, not nanoscale. Because let's think about when you cover 10 micrometer by 10 micro, you just need one 10 micrometer nanosheet, not 101 micrometer particles. And this is, I'm going to skip this one. Then we test a lot on how efficiently allow the current flow in 2 dimensions, because you can see here, this is the result from nanowire, and by mixing nanowire and nanosheet and only nanosheet, it shows line to line result in point contact. Line is line contact. And finally, when you use the copper nanosheet, it shows really nice plane contact. It allows more control compared to the nanoparticle system or nanowire system. This is the real image. It's really look like, A4 paper. So we try to use this one for EMI shading first. So when I watch the lecture on Professor Lin, she used brushy system, right? It allows really high surface energy, but our system is really hierarchical porous system. Then it allows absorption of any, I have no idea actually, some chemical moiety on the surface. So basically we use this one for EMI. So anyway, EMI is harmful, right? So to prevent this one, we use usually the copper foil. When you pop out your cell phone or smartphone, definitely they're gonna use Apple and Samsung as well as other company use 10 micrometer thick copper foil. That is best. But when they use our system, it was really nice because I'm going to skip this one. But most important thing is the EMI. You guys have to understand EMI shielding mechanism, because the EMI shielding is strongly depending on the conductivity. That's why people use the copper. Copper is cheap. Then, if you allow more complicated internal structure, it enhanced EMI shielding performance. So based on this, mechanism, on understanding of this mechanism, let's go move to the next one. So in 2018, people demonstrate the efficient EMI shielding film by using the vaccine. The vaccine is very similar structure with the graphene, right? It's atomically thin, and that formed really multiple structure. So it displayed a really nice performance compared to the copper foil. It was published in Science. So I thought, my system is really much better than this one. So here, right after synthesis our material, then we can just spray out any surface. Then we can get really shiny surface. Then this is copper nanosheet. But when you go pop in South Korea, you can get natural. So this is sometimes called copper natural. Then we can cover any desired substrate. So we can increase the loading weight. Depending on the loading weight, the internal structure is getting generated. So if you allow more porous structure, you can put more. So we studied more natural. I'm happy, right? So we test the internal structure by using XRM. XRM is one of the representative visualized analysis system to check up the porous structure. Then the copper volume is only 34 or 35. The void is 65%. So what I'm saying is really porous and light. It allows really efficient because we save copper, right? This conventional copper void is this much density. Our system is only 3.0. Then this is the release system. So when you heat it up, certain temperature, then each nanosheet is make really good contact. So it allows really nice conduction. Then EMI 3D performance was really nice because unfortunately you guys may think about that it's going to saturate when the loading rate up to 5 millimeters. So unfortunately, we don't have such a good network analyte to measure the high performance. It's a limitation of the test machine. So it has a wide range coverage because this X-band and Q-band is very useful for the military. So now we are working from Department of Defense as well. So I'm going to skip this one. So anyway, this system is really flexible because copper single crystalline is really flexible. Then right after multiple bending, almost 5,000 cycles, the performance is still good. And right before and after, there is negligible change on the surface. So you can see here in between this, copper sheet, it allows really nice transport path of any, biomolecule, whatever liquid, something like that. So this is the result. Even though the copper, you guys have think about that, those is really easy to oxidize, right? But half is true, right? Half is wrong because when we leave our sample in 24 months in air, the surface is definitely oxidized. The color is changed, but you can see here the resistance and EMI shielding is still okay because the copper core is still copper. Then so finally, so you can see here, this is medicine, right? But the early stage of this lecture, I told you 10 micrometer is very important. It's criteria. So you can see here, when you go up here and here, the aluminum foil and medicine here, our system is 10,000 times better than the medicine and conventional copper foil and aluminum as well. So I'm going to skip this one because long-term stability is really important, but I don't have enough time. So I'm going to show you very interesting, assembly method. This is really new. I'm going to those beautiful and yeah. It was published the advanced material this May. So conventionally, when you fabricate any conductive film on substrate, you guys may think about there's some coating method, right? So how about ultrasonic? When you clean up any surface and your glasses, right? You have to put your glasses in ultrasonic. Why? Ultrasonic move away any undesired particle on the surface, right? We use that ultrasonic system. So here is a omnidirectional is non-directional. We can coating everything on the surface. So it is happen only unfortunately in our system. It's copper or silver. So here is we prepare very carefully the two-dimensional copper. But unfortunately, we have to do spray coating process, right? It's easy. Students like easy spray. They just do spray. I push it then. Let's try other method. Then what is the exceptional what else except conventional method? So ultrasonic, I'm going to skip. You guys know what is ultrasonic, right? So when you do ultrasonic, bubble generate and bubble growth and bubble collapse then push away. Then we do ultrasonic. Finally, just put our copper nanosheet in the reservoir. Then we have to carefully select the solvent. Then we put some glass or silicon substrate. We do just ultrasonic. Then you can see here we test nanoparticle, nanowire is only nanosheet allow assemble. The opportunity is really hard time to looking for the reference paper. There was no reference paper. It doesn't make sense, right? So we test a lot. Why? So you can see here, when bubble is growth here, and cavitation bubble is the bubble is increased, then right and collapse is bubble push down the sheet on the surface. But depending on the relationship between surface and the solvent, when you use, we find out when you use, so this is it happen when the copper sheet overlap, there should be some gap, right? The bubble going to be generated here, then it's going to lift off. But when you process this again and again, the nanosheet is going to looking for their proper position. Then we test a lot the relationship between the solvent as well as the surface property of the substrate. Then we find out it is happen with hydrophilic surface with non-polar solvent. So this is the result. When you test a lot of solvent here, this non-polar solvent allow the coverage of copper nanosheet on surface. But unfortunately, when you test any polar solvent, it doesn't allow much. So, and also when in copper oxide, if you can see here, this is quite low. That may generate some space of formation of bottle in between copper nanosheet and the surface substrate. This is the result for depending on the process time and the concentration. Then we can control the selective pattern by using the hydrophobic and hydrophilic surface change by using the phosphoric acid metal samples monolayer. Right at the patterning, we just put our sample in solution, then just do ultrasonic, we can get really nice pattern without any further process. Because when you pattern any metal, you have to do some lithotripsy process or spray or inkjet printing, something like that. So it is also applicable not only copper nanosheet but also aluminum, silver nanosheet. So any complicated structure is possible because there is called omnidirectional. When you put the fiber and the pumpkin or glass something, pumpkin, dolphin, whatever you're thinking, you just put and just press the button, you can assemble copper nanosheet on the surface. So this is a real, this is very simple. This is very short, and we use, it's glass, right? Then this is, you can see here, ultrasonic cleaner, no, Then put a sample here, it takes around 10 minutes, I guess. 7, so okay. And finally, we can get the really nice coating on the surface. It is applicable not only surface and inside and outside, both sides is okay. So, and we test heating. We use this one on the tube, then apply some voltage between this one, so we can adjust, so we can make some heater, tube type heater. So unfortunately, I don't have enough time, right? Time is almost over. 2-3 minutes. I'm very briefly show you. So based on this hierarchical folder structure, we use the reconfigurable hierarchical folder architecture for the 2-dimensional sheet in multifunctional tribal. I think we just put this one by hand or whatever you're thinking is generate electricity. It was just accepted in advanced material. Very shortly, as I'm going to skip this one, I'm going to show you the final result. Anyway, there are a lot of different, the approach to control the surface to generate the electricity, but our approach is very interesting to control the internal structure, but our system is really hierarchical folder structure. Right at the spray coating, our system is really, hierarchical. Then we put in filter the PDMS. So what I'm saying is any liquid can be infiltrated our really porous system. So that's why I think this system is really one of the unique structure for sensing some electrochemical, something like that. So when you increase when you approach the cylinder and we generate something, we can generate the electricity by using this one. So finally, I'm going to skip this one. So what I'm saying is really nice because even though 100,000 cycle is still working well, then it was really uniform. Then it was also working not only on energy harvest, EMI shielding as well as Joule heating. It has three functions. Then we also do this one for the fiber type sensor. So definitely I'm going to use this one for fiber type sensor or generator system. So you can see here we very carefully coating our system on the fiber. Then we do zeta process. Definitely it generates really nice generation of the electricity. So this is a summary. So we demonstrate our key technology is fabrication any electronic device and system on the fiber. Then we do the one more key technology is copper as well as the silver. But so when we produce and synthesize this one, we can produce up to 100 liter scale. So when you synthesize, we can get almost 200 grams. So my collaborator asked me, why don't you give me some powder? Okay, how much you need? They usually expect 50 milligrams, something like that, but I gave them 1 gram or 2 grams. So we can do a lot of tests by using this one, for example, some antibacterial film, something like that. And silver. So a lot of people ask me, have you ever tried silver? Yes, we do. And we can control same dimension, same structure. So it's now, unfortunately, I don't have enough time to introduce this one. We recently under revision for one of another advanced material paper by using this one for stretchable electrode. It was really nice. So this is my student, and I'm really thanks to Kim, a lot of Kim, including me, Kim, and this is funding source. And it's really hard to say in Czech.
Moc děkuji.
Yeah, but you can thank you for your attention and arigatou gozaimashita. And 谢谢 and 감사합니다. Thank you so much.
Thank you. Thank you very much. Very interesting presentation. Questions?
So we have a lot of time to
Yeah.
question.
I have to ask at least one.
Yes.
Like
Please.
you've shown the electronics, or let's say chip on the fiber.
Yeah.
How about the temperature
Sensors.
No, just asking. There are different materials. They have different temperature coefficients. So how they are aligned together to let's say break somehow. How does it work? Did you measure?
So temperature sensor
No. Not just the chip
on the fiber.
On the fiber.
Oh yeah, I think this is
There are different materials,
Yeah.
I suppose. So they have different temperature coefficients, and probably it could lead to some misalignments according to the temperature.
Yeah. So when we fabricate this one, I'm not fully understand what you are saying, but the reason why we choose the quartz fiber because we do thermal annealing right after deposition of the indium gallium zinc oxide.
So this thermal aligning helps to accommodate the different materials.
Yes, right.
Okay. Understand.
So everything is done based on the conventional lithography system.
Okay.
Yeah. So if we resting, but if we have special machine, we can do in continuous system. That's why now we have a strong connection with Professor Thomas Gries in Aachen University in Germany. So we try to develop some system for the continuous fabrication because his team is really oriented to production of fiber. So we have technology on the integration. So I'm sincerely looking for the collaborator with you. The application of this one for some sensor or so on this kind not that much normal system. Yeah.
So another topic for the discussion. Thank you very much, Mr.
Thank you.
And for the morning session, let's have 1-2 minutes for the refreshment before we will prepare the presentation. This one, right? You will have the two card. So just give them 1 minute for the coffee and we will continue. Okay. Don't worry, we will not shorter time. Okay. So, yeah. Yes, it's good. Okay, so please prepare your coffee or tea as fast as possible, and let's proceed. Last but not least, lecture for this morning session. Okay, so let me introduce next lecturer, Professor Genki Yoshikawa from University of Tsukuba in Japan, another distinguished guest here, and I suppose another quite interesting lecture and presentation. So, Genki, the floor is yours.
Okay. Thank you very much for giving me a chance to this introducing our recent activities on olfactory sensors. And I'd also like to thank Vivian for some arrangement. Okay, so today I would like to talk about this olfactory sensor. So this is kind of gas phase sensors. So I hope some of you may get interested in this type of sensors and get involved in this exciting field. Okay, so today I would like to talk about these contents, like to introduce some odors, general introduction of odors and olfaction, and overview and of e-notes, electronic notes, so olfactory sensor, and our sensor MSS for some research and development and recent biological gas measurements. Okay, before going into these contents, I'd like to show some background of myself and our institute. So I was working in kind of surface science, and when I moved to when I had the chance to move to University of Basel, then I started kind of olfactory sensors. And okay, then for NIMS, so my primary affiliation is this NIMS, National Institute for Material Science. So, and served also as a professor in University of Tsukuba. Okay, so this NIMS is located close to Tokyo, just an hour. Yeah, so, but some of you may not know this NIMS. So national something long name, so please remember as NIMS. Okay, NIMS has lots of activities in terms of academic papers and also largest patent licensing income. So it's far ahead of other research organizations in Japan. So we are trying to make a practical something. Okay, and also we have lots of collaboration with various universities, and we are also looking for passionate students. And you can, we can support your life in our universities. And also, from this April, the Crown Prince of Japan enrolled at this university. So it's kind of regarded as a royal university. Okay, anyway, let's get started for this introductions. Odors or smell. So what are these things? So it's very thin, super thin, and super complex, and always fluctuating. So we need to have a good sensor with high sensitivity and selectivity and reproducibility with quick response. Okay, to look in to understand more about this odors, let's get a deeper view of this first thin part. So how thin it is. So this is a typical contents of air composition. You know, mostly nitrogen and oxygen, and some others. And in this log scale, you can see the stinky odors range like this level. So it's quite thin. But our nose can recognize these stinky odors very quickly and very significantly. Yeah, so this ppm, ppb, and ppt levels, it's kind of one eye drop in 20 Olympic pools. It's a bit difficult to imagine, but our nose still works like that. So we are trying to make some sensors like these ranges. Okay, and super complex. As you may know, odorous molecules, there are lots of odorous molecules, and one molecule, so this coffee flavors, contains a few hundreds of different molecules. That makes the unique odor of coffee. And our breaths are supposed to contain more. Okay, then if we simply calculate these numbers, like out of 400,000 different kinds combined to thousands of them, then it gives this huge number, and it's quite difficult to imagine. Yeah, but anyway, so then always fluctuating. Okay, I would like to show one example how these guys are fluctuating. So in this so-called Schlieren measurement, I tilt this bottle and let the vapor pour out of the bottle. As you can see here, so I'm not dropping the liquid, but dropping the vapors. So it fluctuates a lot. And more importantly, so that Schlieren measurement was done here. So I just dropped a few seconds of vapors. Then here we have our PTR TOF mass spectrometer. So it's a very highly sensitive gas analyzer. And these two are about 10 meters apart. But after dropping this acetone here, then about a minute later, these guys start detecting the acetone vapor. So it propagates a lot around. And this dropping of vapor makes the entire room acetone concentration about 300 ppb from the baseline of few ppbs. So as soon as you drop something or generate some vapors, it fluctuates and propagates a lot all around our environment. Okay, so we have to detect something like that. Okay, then olfaction. Olfaction is regarded as the last sense in the five senses, and some of you may regard it as a kind of least important sense, but actually, the olfaction is critically important for humans or all other organisms. So this is one statistical study that mortality risk factors. So this anosmia is dysfunction or loss of your olfaction sense. That makes the mortality risk quite high compared to cancer or heart attack, diabetes, and so on. So if you lose your olfaction, you may have a high risk to your life. Okay, and another interesting feature of our nose is very high selectivity. This is the optical isomer of a famous molecule called limonene. It smells like lemon. But if you have optical isomer of this lemon flavor molecule, it smells like orange. So this very subtle difference makes very different sense of smell. Okay, and also this is one famous molecule called beta ionine, and it smells like a kind of flower. But genetically, our nose has different performance, and half of Japanese people has a certain gene, and with a single difference in our DNA, this one amino acid will be different in this protein. So this is the olfactory receptor protein. So this single difference makes the sensitivity 100 times different. And this kind of individual variations happens for many different molecules like this. So this is beta ionine, and some guys can recognize at 0.1 ppb level, but some people cannot recognize this smell until it gets 10 to 5 orders of magnitude. So I'm in this range, so it's very low sensitivity to these molecules. Okay, so and this trend can be found in different regions in the world. For Japanese people, this beta ionen, half of the people will have a high sensitivity. But if you go to Africa, more than 80% people have higher sensitivity. And we are in Czech, so maybe kind of similar to Japanese people, but a bit more sensitive than typical Japanese. And this kind of difference can be found all over the world. And for the same odor, people's perception differs by over 30% on average. Okay, and this is also interesting report that maybe some of you know that natto. Natto is a fermented stinky bean. But some of the German people smells this roasted tea. It is my favorite tea, and it for German people, it's quite unpleasant flavor. Whereas for Japanese people, it's a very pleasant flavor. So this kind of very different perception can happen in historical, rheological, and many different factors. Okay, so this is a kind of overview of odors and olfactions, and in short, it's quite complicated. So we have to combine not only sensor development, but for some data analysis and some more comprehensive approaches. Okay, then how about the e-noses, olfactory sensors? As I said before, the 5 senses has their corresponding sensors like camera, microphone, and so on. And for smells, it's still not yet standardized or still developing. But these kind of chemical sensors are expected to contribute to new generations of emerging fields and important fields. And it's then where our e-nose can contribute in which way. The important aspect of e-noses are non-contact measurement in real time with low-cost device. So if we cannot utilize these features, it may be not efficient way of using e-noses. And also, we have to have some closed, so we can access the closed space or biochemical reaction. So these are not accessible for typical camera or some physical sensors. So we have to think carefully about the effective way of using e-noses. So actually, there are lots of inquiries almost every day that the potential application of e-noses. And yeah, some of the may be possible, but might be difficult at this moment. But anyway, we always have to keep in mind that some features and effective way of using these sensors for real practical application. So, but as you can see here, there are so many potential applications. So the olfactory sensors looks like a perfect and attractive blue ocean market. So many researchers, companies try to get into this blue ocean. And actually, it is very perfect and attractive. But we have to be careful that there are so many dead bodies at the bottom. So we also dive into this ocean, and we enjoy it for a while. But when we carefully review all the histories and so on, we found that so many dead bodies. So it's we have to be very careful about how we can develop in practical way. Okay, so actually the history started from already in 1980s, and after in this 40 years, there are so many devices, researches, and papers, thousands of millions of papers published. But so far, it's not yet well implemented into our society. And actually, already in 2008, there is some well-cited review paper introduces lots of different real products of olfactory sensors in a long table. But most of them just disappeared. It's quite difficult to maintain this market or some this kind of activity. Okay, but there are some successful commercialization, so we can learn some tips from here. So a successful commercialization case one is the breath-based asthma diagnosis. As you may know, if we have some inflammation in our throat, there is some nitrogen oxide comes out. So if we measure this NO carefully, we can diagnose whether we have some inflammation or not. So actually, there are some devices, and these devices are officially now covered by National Health Insurance. So it's real medical device. But these devices are not developed in quickly, but it took about more than 20 years of development. From so the paper published about nitrogen oxide in 1991. So after that, so many development. And I looked into the technical details of this device, and there are so many integration of many technologies, not only sensors, but many peripheral parts. So we can learn that we have to have a clear application and clear target analytes with scientific evidence and comprehensive optimization of components. Okay, another successful case is the explosives detection sensors. And actually, the basic technology was developed by Professor Slager's group. And he's, you know, some of you know that he is a big name in the organic synthesis. And there are so many alumni in NIMS. So he sometimes visited, and he also kindly visited our group. And he actually made a very sensitive sensor for detecting explosives. And you can look into some websites, but it's not so well described because it's already really working in the military and also really in the airport and so on. So real successful products will not advertise a lot. Actually, it's already working. They don't need to advertise anymore. So anyway, it is now looks like this. And the point of this device is that they utilize quenching phenomenon. So once target analytes combine to a certain part, it quench the fluorescent light that was emitted before absorption of this target analyte. And if they take these parts together and make a polymer, then a single absorption of target analytes will quench all the fluorescent light from this whole polymers. So this is a kind of enhancing amplification trick for high sensitivity. Yeah, absorption of analytes will quench the fluorescent light. Then they integrated that structure into this capillary waveguide with some polymer film coated inside. Then yeah, it works like this when you have some analytes inserted into this ports, and if no threat found, then so the baseline will have some certain fluorescent light, and if it does not quench, then it is judged as no threat. But if some part of the fluorescent light quenched, then it is regarded as threat found. So in this case, again, there is a clear application, of course. Then clear target analyte that is actually explosives. And sensing layer engineering and optical detection. So these are kind of general tips for any type of sensors that we have to have some sensitivity enhancement, some amplification. So especially for if so, in this case, polymer quenching and the optical detection. So for optical detection, we can always use that multiplier that can enhance the sensitivity up to 10 to 6, 7 orders of magnitude. So if you can transform your signal into an optical signal, you can quickly gain 10 to 6, 7 amplification, and also some sensing layer amplification. Altogether, you can gain 10 to 10 or more amplification from a single event. So it's quite important. Without this amplification, we have to compete with these technologies with simple amplification. Anyway, our sensor is not using this optical approach, but yeah, if it is possible, then we can gain a lot. Okay, so these are the histories, and so we can there would be a possibility to make some new devices to contribute a certain application. Okay, then let's go into this MSS part. So the olfactory sensors can be regarded as a combination of these components. So first we have some analytes and receptors, and some signal will be transduced into electric signal and some information. So we have to first have some good sensor to make our own sensors. Okay, so for the practical factory sensors, we try to make a good sensor platform. So I'm very lucky and happy that to have some collaboration with Dr. Loader, who invented that STM, and Dr. Akiyama Teru. He had a god hand in MEMS fabrication, and Peter. He led various big project in Zurich. Okay, and we integrated all this mechanics, materials, and crystallography and electronics to make a new device. So here is the summary of our development of our sensor. I'm not going into detail, but just briefly, we have this a nanomechanical sensor, and in that sensor, we have to detect some surface stress generated on the surface of this structure. So usually, a cantilever structure is used. But in this case, if we want to detect this sensing signal with electrical way, not laser reflection like AFM, we have to have piezoresistor embedded on this structure. And those piezoresistor have some tricky features, like the stress in this X direction and stress in Y direction. So this direction have so the difference between these direction stress will give signal. So we started with this typical cantilevers, but eventually we found if we prepare a larger structure that capture the analytes and generate the surface stress, then this structure bends toward the free end. Then if we connect the tip with another sensor, then we can induce point force at the end of the tip. So we can gain this one with almost zero of this one. So we can gain a lot of signal. Then we eventually make this fixed part onto the opposite side, and then finally to this field membrane structure that capture all the induced stress around the membrane. And we also integrated with the electrical features of this sensor. And then finally, this membrane type surface stress sensor, in short MSS, was established. So with this structure, we have very high sensitivity and small size with MEMS process and versatility. It means we can use whatever materials as a sensing layer. And as you can see here, that it works like this with a receptor layer coated on the thin silicon layer, and with absorption of gases, it mechanically swells and induces mechanical stress on the piezoresistors. Okay, so this is a real-time observation of MSS working observed under the microscope, digital holographic microscope. And when I blow my breath, it reacts as expected with different types of polymers coated in this case. Okay, then, so this MSS achieved more than 100 times of higher sensitivity. Yeah, so this is now commercialized, so anybody can purchase this sensor chips. If you want to use your own receptor materials, you can purchase from our collaborator Akiyama-san Tel. And we can also provide our sensor with receptor layer from our own startup. Okay, so based on this MSS, we have been working on basic towards implementation and starting from analytical modeling and materials data analysis and industrial collaboration and our own startup. And we are now focusing on this biological gas measurements. Okay, I will briefly overview these topics. Okay, from the basics, Kosuke and Gaku, they are working hard to make an analytical model of our sensors. And finally, we can we establish the analytical model for sensing signals, and we can reproduce a sensing signal. And here one example of the analytical importance of analytical model. So in the case of this type of so nanomechanical sensor with receptor materials is a kind of categorized as the equilibrium-based sensor. So we are measuring equilibrium of between gas and solid. So in this case, this different molecules with similar lengths, the saturation concentration is more than 50 times different. But still, the sensing signal are almost the same, at least in the same order. So actually, this is understood by analytical modeling, and this is in the case of alkanes. And anyway, the sensing signal is proportional to partial pressure.
Just a short. I need to use them.
No to je seminární skupina, to se přihláší jenom.
Oh, okay. 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 Great. Yeah. Oh, okay. Anyway, we have to be careful that if we focus only on the concentration, then there are many papers that reports high sensitivity with in terms of concentration. But for this type of sensor, we are not measuring the absolute concentration, but we are measuring the partial pressure. So we have to be careful. And the basic theory is already published in 1998. But yeah, sometimes we miss this basic working principle. Okay, anyway, if we have good receptor analytical models, we can get more purified information from our sensing signal. So in this case, Kosuke and Joe try to differentiate this nonana and nonena. This is known as aging smell. So we want to differentiate this one from this one. But it has similar structures and various concentration and various humidities, whether we can differentiate even with these difficulties. So these are the analytical models and extracted parameters from analytical model. And this signal amplitude corresponds to the sensing signals intensity. And for this time constant regarded corresponds to this shape of the sensing signal. So with these polymers coated on the sensors, then we measured these gases and found that this signal intensity clearly correlate with concentration as expected. And also, we confirmed that the time constant can differentiate these gases very clearly. Then even so, if we extract some random, not random, but some points from the sensing signal and made a simple principal component analysis, then some gases overlap because of the mixture of this information of this one and this one. So with analytical model, we can separate the information from the concentration and time constant. Okay, and with this one, we can also get a robust sensing features, even with different relative humidity. And we can clearly differentiate with nonena and nonana, even with different concentration and different humidities. Okay, and some materials development. So actually, any types of materials can be used as a receptor layers, and this receptor layer determine the performance of our this kind of sensors. So if you have any good materials, please let me know that we can quickly try your materials, just drop and measure. So it's in quick experiment, we can test your material. And it can be nanoparticles or biomaterials, 2D materials, metals, and so on. And if you are interested in, Kosuke summarized our recent activities on also receptor materials. Okay, then I like to show some unique receptor materials. It is for DNA. So as you know, DNA is highly hydrophilic material, especially with phosphate backbone. So in this case, Tomohiro and Kosuke made a great experiment that put a DNA as a receptors and measure the contaminated water in the organic solvents. So water contamination in organic solvents makes a huge mess in the organic synthesis. And usually we use a Carl Fisher titration to measure the water contamination. But in this case, we can simply detect, measure the vapors of this solvent and detect the water, even in a trace amount of water. So we developed a Bluetooth module that can be attached onto directly to this bottle, and we can detect the trace amount of water. And we compared with the QCM and with same conditions. And it is found that this nanomechanical sensor can measure more than 1,000 times higher sensitivity because it is kind of repulsive mechanical reaction on the surface. It's not not so many molecules absorbed, but the mechanical repulsion induced by absorption of water makes this huge sensitivity. Okay, and another interesting material is gold nano cage. Yeah, this unique structure makes a different electronic structure on the surface of this material. And this gold is a quite robust material, but we can still make a different electronic states, and that can be used as a robust receptor material for differentiating various chemicals. Okay, and for the data analysis, we also made various approaches. Okay, so this is just a general caution that so in this case, we just prepare the random number, 200 random numbers, and put random labels on those numbers, and make a linear discriminant analysis, one of the supervised analysis. And in this case, even with random numbers, under a certain conditions, it can be differentiated. So we have to be careful about this kind of misleading AI analysis. Anyway, the first example is a quantitative prediction of specific information. Yeah, Kota and Liu made this study. And first, if we try to differentiate the components mixed with more than 3 components, it is known as a very tricky and difficult task. So we try to integrate the AI or machine learning approach to get some information out of this complex mixture. So in this case, we try to predict the alcohol contents from the odors of liquors. And first Kota prepared the nanoparticles and measured different types of liquors. And Liu made machine learning models and makes feedback for material selection. We started with nanoparticles with different functional groups on the surface, and confirmed that these combinations can differentiate different types of chemicals like this. Then we measured the liquor samples, in this case, 35 different liquor samples. And this is a typical sensing signal. The gas injected and parsed 5 times. And in this case, these are all 40% liquors. So if we only focus on the signal intensity, it's kind of impossible to differentiate these things. So we extracted these 4 features from our sensing signals and found its alcohol content and the parameters relation. So this look very random, so it's not good features, but these are positive relation, negative relation, and so on. So with these features, we made a machine learning model and evaluate the prediction error. And as you can see, these 2 materials, it has a big prediction error, but these 2 have low prediction error. So in this case, these are kind of hydrophobic material, and these are hydrophilic materials. So we simply replace these hydrophilic materials with hydrophobic polymers. And finally, we got this very clear prediction model that can predict the quantitative amount of the specific contents, in this case, alcohol, ethanol, with the prediction model. And to make this feature extraction more effectively, we are recently working on the explainable AI. And in this case, we use CNN for detecting making the prediction model. And with this explainable AI, we can find that which sensor at which time these prediction, the sensing signal contribute to the sensing prediction. So yeah. So with this kind of technique, we can make some prediction model more effectively. Okay, so yeah, some other examples, but I like to skip these parts. And some tricky problem for olfactory sensors. Yeah, but okay, then maybe this part also takes some time. So I'd like to show some biological demonstration. So yeah, we have collaborated with industries and many companies, universities, and involved. And with these activities, we acquired lots of know-hows and technologies. Then we are making some devices like this. And this device includes all we need for the measurement. And it is now available. And if you are interested in, we can provide these devices, and you can try whatever material deposit and measure some gases for various applications. And based on these technologies, we are now operating our own startups to facilitate these practical implementations. Yeah, okay, then based on these technologies, we are now focusing on this on-site demonstrations, especially for biological gas measurements, and focusing on agricultural applications and medical applications. So for the first agricultural applications, we have been collaborating with National Organization of Agricultural Research. And we try to monitor the health condition of cows by measuring smell of milk. And we first started with a large-scale trial with 70 milky cows. And we expected clear correlation between blood biomarker. So this is an established biomarker called beta hydroxybutyrate with some volatile component with some clear correlation like this. But as you can see, there is a very big individual variation. And so this is not only the case for volatile components, but the same molecule in blood or in milk. These two still have large variations. So it's intrinsically difficult to monitor this kind of biological markers with a kind of snapshot. So we try to focus on the individual cows to compensate these individual variations by a time series measurement. And we made a blood test, and some specific cow got sick and recovered. Meanwhile, we also measured the smell of milk by our sensor, and we confirmed that we can clearly monitor this trend. So we tried to make this kind of time series individual measurements at the real farm. So we went to this actual farm for 3 weeks and tried to make these measurements. So we constructed our own automated milking measurement system working with milking robot behind. So it's a huge system. And we confirmed that even at the farm, we can still measure our signal, and consistent with a blood test and chemical milk test. And we confirmed with all the 4 tested cows. And yeah, so if we can monitor this trend, we can so if this health condition goes wrong, then the yield of milk reduced like this. So if we can make some alert at this onset, then we can avoid this kind of milk yield drop. So we are now making a real product out of this technology. Okay, for the medical applications, we first measured the breath of the cancer patients and healthy person, and observed that we may be possible to differentiate these two. But at this moment, more than 10 years ago, together with the University of Basel team and EPFL team, the numbers of patients are a bit limited. So we try to confirm whether this technology can be really implemented into the hospital. Then we collaborated with 2 big hospitals in our region, Professor Kojima and Professor Sato's group. And yeah, and working together for more than 10 years. Then first we tried to establish the breath collection and measurement and analysis protocols. And actually, it was so hard to find the best condition. So it took more than 3 years to establish the reproducible measurement and analysis protocol. But this Nada-san, together with yeah, so together with other team members, we finally established the very reproducible protocol. It can give a highly reproducible signal throughout a year if we measure in the same condition. Okay, then again, it is something like the similar time series measurement that we ask the patients to provide their breath before and after surgery. Then we built a prediction model for lung cancer detection from these measurement breath samples. And we measured about more than 60 samples, and for all combinations of all sensors, we plotted the accuracy of each combination. And we found that a certain combination of sensors can give a detection accuracy of more than 80%. So with this result indicates some possibility of using this type of sensors to detect lung cancer for some screening. But actually, it is still quite kind of black box. We are not sure about the actual biomarkers, and in the worst case, it may be detecting something different. So we are now trying hard to identify the real breast biomarkers for cancer detection. And actually, that is a long-standing issues for this kind of breast diagnostics studies. Okay, so with this time series measurement, we can monitor milk's cow's conditions, and we can demonstrate some possibility of lung cancer detection. Okay, then just some tips for eNose. Yeah, actually, we have been trying to make real practical applications and practical devices. And it is quite important to know the targets and know the sensors. And as I showed in the list, there are many potential applications, but in some cases, the target analytes are in the PPT or even lower ranges. So in that case, it's quite challenging to make sensors for that range. But some targets can be more than ppm. So in that case, it's literally million times easier application. So it's quite important to know the target. And also, of course, we have to know our sensors, how it works. And we also have to think about the selection of sensors. Actually, if we increase the number of the different type of sensors in an array, and if there is some drift, for example, about 10% of drift, if we assemble 20 sensors in an array, it can make a prediction error of 70%. So it's kind of challenging. So we have to select efficient, proper sensors. Then this is some example of the proper number of sensors. 5 sensors. If we reduce to 2 sensors, it starts to lack the information. But if we increase the number of sensors, sometimes it captures more noises. Then it starts to affect the results and mix up the results. And also, we all have to think about the sensitivity and linearity range. In this case, sensor 1 can go down to lower concentration with some linearity. but above a certain concentration, sensor 2 can be much more sensitive. So we have to carefully select our proper sensor in an array to get reasonable signal. So based on the basic working principles, each sensor has their own good part that can cover. So we always have to think carefully about which sensor for which application based on their working principle. Okay, and also, of course, we have to make a calibration. Even with these expensive gas analyzers, it always calibrates. So we always have to calibrate our sensors to gain robust signals. Okay, so if we summarize the challenges in e-noses, so the sensing element, sensors are still weak. So we are always looking for a new type of sensors for better sensitivity and selectivity. And for the system, it's always very hard and so many dedicated optimization required. And for the business aspect, it's quite tough to make real product out of this kind of new technology. And also, we always face this ongoing, everlasting problem. So we always have to take care of this stuff. But with this one, we can make many applications with this type of sensor. Okay, and for the ultimate goal of this e-noses can be a world peace. So here I cited some sentences from English writer George Orwell. He said that smells can lead to some instinctive hatred. So if we can understand something, we can somehow overcome those challenges. But he said that some physical repulsion, so cannot. So this happens because we don't have e-noses that everybody can use. So even at this moment, we have to perceive some smells by our noses and just intuitively understand. But if we can develop the olfactory sensors that can be used for everybody, maybe integrated in the smartphones, then we can now understand what the meaning of that smells. Then we can categorize the smells like some religious difference or education difference and so on. So yeah, I believe that this type of research and development can eventually lead to the contribution to the world peace. Okay, so I would like to thank all the supports with many sources and collaborators all over the world, and hopefully olfactory sensors can contribute to make a better future. Okay, thank you.
Thank you. Let's start another interesting lecture. One question before we go. Okay, so maybe we can discuss it later on. Everybody's under it since. So once again, thank you very much. And now we have about 45 minutes approximately to have the lunch. It is already prepared in the other room. on the left side of the main entrance to this corridor. So general meal, and we will start approximately 13:30, so 1:30 p.m. Enjoy.
It's over.